Good morning, grade 11. Hope you are all doing well and being safe. This is Miss Pamela giving the physics course. Today we are going to start a new chapter. We are going to take section 1 in chapter 7, which talks about planetary motion and gravitation. So please open your books on page 178 and follow up with me. First, we are going to talk about some early observations about planetary motion, which is the motion of planets. In ancient times, the sun, the moon, the planets, and the stars were assumed to revolve around Earth, so ancient scientists thought that Earth was at the center of our galaxy. Then, Nicholas Copernicus, a Polish astronomer, concluded from his observations in the 1500s that the Earth and other planets revolve around the sun. So in the 1500s, Nicholas Copernicus concluded that the sun is at the center of our galaxy and not Earth. But he incorrectly assumed that planetary orbits are circular. So he assumed that planetary orbits are circular, which is incorrect. Then Tycho Brahe from Denmark realized that the charts of the time did not accurately predict astronomical events. So since those charts did not accurately predict astronomical events, then there must have been something wrong with Copernicus's conclusions. He recognized that measurements were required from one location over a long period of time. So in order to come up with correct conclusions, Tycho Brahe recognized that measurements were required from one location over a long period of time. This is why he went to the Danish island of Hven, where he did those measurements. In the year 1600, Tycho moved from the Danish islands of Hven to Prague, where Johannes Kepler, of German nationality, became one of his assistants. After Tycho's death, Kepler continued to study his data, and after 7 years of careful analysis of Tycho's data, Kepler discovered the laws that describe the motion of every planet and satellite, natural or artificial. Now we are going to talk about Kepler's laws of planetary motion. Kepler's first law. So Kepler's first law states that the paths of the planets are ellipses with the sun at one of the two foci. So planets do not move around the sun in circular path, they rather move around the sun in elliptical path. This is what Kepler's first law states. And every elliptical path has two foci. In this case, the sun is at one of those two foci. As you can see in the figure in front of you, it shows the elliptical path of a planet around the sun, and it shows that the sun is located at one of the two foci of this elliptical path. Although exaggerated ellipses are used in diagrams, Earth's actual orbit is very nearly circular. So, orbits Earth around the sun is very nearly circular, but it is not a perfect circle. It is an ellipse. But it is not like the one you see in the diagram in front of you, because this ellipse is exaggerated. Earth's actual orbit is very nearly circular, but it is not a perfect circle. It is an ellipse with the sun at one of the two foci of this elliptical path. Kepler's second law. Kepler's second law of planetary motion states that an imaginary line from the sun to a planet sweeps out equal areas in equal time intervals. As you can see in the figure in front of you, this figure shows the elliptical path of a planet around the sun. The sun is at one of the two foci of this elliptical path. Now we are going to take two equal time intervals. From P1 till P2, this is the first time interval, and from P3 till P4, this is the second time interval. If we draw imaginary lines from the sun to the planet at each one of these time intervals, we get two areas, Area 1 and Area 2. Area 1 is equal to Area 2. This is what Kepler's second law states. Kepler found that the planets move faster when they are closer to the sun and slower when they are farther away from the sun. So planets do not move at constant velocity all the time. They move faster when they are closer to the sun, and they move slower when they are further away from the sun. Kepler's third law. Kepler's third law of planetary motion states that the square ratio of the periods of any two planets revolving around the sun is equal to the cube of the ratio of their average distances from the sun. As you can see in the equation in front of you, this is Kepler's third law. Let's say we have two planets, planet A and planet B. The period of planet A is TA, and the distance from the planet to the sun is RA. The period of planet B is TB, and the distance from planet B to the sun is RB. Let's note that the period is the time it takes for the planet to complete one revolution around the Sun. So Kepler's third law states that the square ratio of the periods, which is equal to Ta squared over Tb squared, is equal to the cube ratio of their average distances from the Sun, which is Ra cubed over Rb cubed. We must note that Kepler's third law applies to any two objects going around a third central object. So it may apply to two planets going around the Sun, or it can also apply to two moons going around a planet. So in Kepler's third law of planetary motion, which is Ta squared over Tb squared is equal to Ra cubed over Rb cubed, Ta and Tb are the periods of the planets, the time it takes a planet to complete one revolution around the Sun, which I already stated. Ra and Rb are the planet's distances from the Sun. Note, the periods must have the same unit, so there is no one unit for the periods or the distances. They must have the same unit. It may be seconds, in days, in hours, etc. And also the distances must have the same unit. It may be meters, kilometers, etc. By cross multiplication of Kepler's third law, we get the following. Ta squared times Rb cubed is equal to Tb squared times Ra cubed. So the period of the first planet squared times the distance from the second planet to the Sun cubed is equal to the period of the second planet squared times the distance of the first planet to the Sun cubed. By rearrangement, we can find the period of the first planet using the equation you can see in front of you. Ta is equal to radical Tb squared times Ra cubed over Rb cubed. We can also find the period of the second planet using the equation you see in front of you. Tb is equal to radical Ta squared times Rb cubed over Ra cubed. Ta is the period of the first planet. Rb is the distance from the second planet, to the Sun, and Ra is the distance from the first planet to the Sun. By rearrangement of this cross multiplication, we can also find the distance from the second planet to the Sun. Using the equation you see in front of you, Rb is equal to cubed radical of Tb squared times Ra cubed over Ta squared. Tb is the period of the second planet, of which we are finding the distance from the Sun. Ra is the distance from the first planet to the Sun, and Ta is the period of the first planet. Finally, by rearrangement of this cross multiplication, we can also find the distance from the first planet to the Sun using the equation you see in front of you. Ra is equal to cubed radical Ta squared times Rb cubed over Tb squared. Ta is the period of the first planet, of which we are finding the distance from the Sun. Rb is the distance from the second planet to the Sun, and Tb is the period of the second planet. It doesn't matter which planet you choose to be A and which planet you choose to be B. As an example, we are going to solve example problem 1 on page 181. So open up your books and follow up with me. Example problem 1. Callisto's distance from Jupiter. Galileo measured the orbital radii of Jupiter's moons using the diameter of Jupiter as a unit of measure. He found that Lo, the closest moon to Jupiter, has a period of 1.8 days and is 4.2 units from the center of Jupiter. Callisto, the fourth moon from Jupiter, has a period of 16.7 days. Using the same units that Galileo used, predict Callisto's distance from Jupiter. So here we do not need to convert any units. We need to use the same units that Galileo used. First, we write the given. We must note that here we have two moons orbiting one planet, so we can use Kepler's third law of planetary motion in order to predict Callisto's distance from Jupiter. So we have the period of the second moon, which is equal to 16.7 days. We have the period of the first, which is equal to 1.8 days, and the distance from the first to the planet, which is equal to 4.2 units. In order to find the distance from the second to the planet, which is Jupiter, we use the equation that I just stated in the previous slide. Rb is equal to cubed radical Ra cubed times Tb squared over Ta squared. So we replace these unknowns by their magnitudes that are given in the problem, and we get the final answer, which is 19 units. So Callisto's distance from Jupiter is equal to 19 units. We have the distance from the first moon to the planet, which is Ra, we have the period of the second, which is TB, and we have the period of the first, which is TA. So we do cubed radical RA cubed, times TB squared over TA squared, and we get the final answer of 19 units. As a homework, please solve numbers 2, 3, 4, and 5, page 181. Notes, Earth's period is equal to 1 year or 365 days, of course, because this is how much time Earth takes to complete one revolution around the Sun. When they ask you to find the answer as a multiple of Earth's distance from the Sun, then the answer is a combination of a number and or Earth, which is Earth's distance from the Sun. Your homeworks must be done and submitted to me on Tuesday, May 5. Thank you, good luck, and stay safe.